Okay, so in the lectures yesterday, we talked about basically mostly about the new physics searches. So my plan is today we are going to switch gear. We'll talk about a little bit of precision measurement and at LHC you can do, and so tomorrow we'll talk more about dark matter searches at LHC. Okay, so so the motivation for precision measurement is well, I mean, we always wanted to measure things more precisely, but at LHC, at the beginning, you may not think it's a precision measurement machine. So because it's a, we wanted to build it as a machine that directly search for new particles. So that kind of search will still go on. So and on the other hand, as I argued on my first lecture. And so we're approaching to some slow gaining era of LHC. So the reach for the direct search are only going to go slowly with luminosity from now on. And on the other hand, we'll have lots of data. Okay, so there are still 99% of the data from LHC according to the plan. And so one thing you can do very well is probably to try to measure something as precisely as possible. Okay, it's still true that measuring things at hadron colliders are difficult, but we need to do our best. You see, it is still difficult, but we can actually do something. A very obvious target for precision measurement is the measuring the property of the Higgs boson. Right, so the well, mostly because we don't really know the property of the Higgs boson very well. So that's the reason. So and it's a newly discovered particle. We wanted to understand it as much as possible. Okay. So, but it for any precision measurement, it's very well. Of course, we wanted to know everything as much as possible. But usually, it's useful to have some target in mind. Okay. You think what we should be aiming at. Okay, so let's see. So Higgs measurement, we will have what is the target. Okay, we will be try to measure some deviations of try to aiming at constraining the deviations from standard model predictions. On the other hand, so the deviation will typically enters. So what is the typical size of the deviation? Suppose induced by new physics. Okay, it comes in with this form. So roughly, okay. Okay. So it's coming from dimension 6 operators. Okay, that's the lowest dimensional operator that we can write down to correct Higgs couplings. Okay, and so this is the mass of or the scale of new physics that you integrate out, and then this is the electroweak VAV. Okay. Now, on the other hand, LHC direct searches. Direct search also will look for these new physics particles, right? So direct search already, or is going to cover, is going to constrain, for this in general to be greater than or equal to a TeV. Okay, at least about a TeV, it's going to be constrained, or many of them has already been constrained. Okay. So if you put a TeV here into this formula, you roughly see 5%. Okay. So this means that in general, we don't really expect deviations on Higgs couplings to be much bigger than this size. Okay. So it's probably okay. Therefore, in order for the Higgs coupling measurement, at least to be, comparable in sensitivity to the direct search, and this is a number to be aiming at. Okay, at RHC. Now this is not a theorem. Okay, of course I can. All of us can write down models that somehow this is small, but so the deviation is bigger, and yet it can evade Higgs evade RHC searches. Okay, that is obviously possible. This is just a generic statement. Of course, there are lots of exceptions, but it's good to keep this number in mind. It's just a rough target. And this also means that if I cannot measure some coupling down to 5%, but I should still do it. Okay, even if I can only measure it down to 10%, it's not a waste of time. You should still do it, but it will be great if we can get to this level. Okay, so that's the target. So what kind of Higgs couplings we wanted to measure? Okay, so so there are the Higgs coupling to W and Z. And there is a Higgs coupling to fermions, right? different fermions. And so standard model predictions, the standard model has a specific predictions for all of these couplings. Okay. And there are additional Higgs couplings, such as this. Okay. And so in standard model, these are coming literally from the same coupling. Okay. So you just depends on how many fields you depends on how many VEVs you wanted to have. Okay. And there are also couplings like this. Okay, 3 Higgs bosons and 4 Higgs bosons. Okay. So for the moment, well, at least at the RHC, we will not worry about this. Okay, it's very difficult to directly measure that. Okay, at the RHC, and it is completely impossible to measure this. Okay, well, you can try, but if you have maybe you have a better idea, but the people tried, it's very difficult to think about these couplings. And this one is very problematic. Okay, so this one is actually a very interesting target to try to get to this one, but at the RHC maybe we should be able to get down to some order 1 measurement. Okay. Well, certainly we haven't seen this coupling yet at the RHC. Okay, but even eventually we may be able to see some evidence of the existence of this coupling. Okay, that is what that is this order 1 means. Okay, so and these guys are our main target. Okay, at the RHC. Also, now there can be many fermions. Okay, there can be many fermions. So there can be TT bar, BB bar, tau tau, mu mu, EE. Okay, there can be those. And also, charm, CC bar, and the U and the D. Okay. All right. In principle, there are all of these things. Okay. And at the RHC, this is impossible. It's too small. Okay. So let me just you probably know this. This coupling in the standard model looks like this. Okay. So for electrons, it's suppressed by the small fermion mass. Okay, this coupling. Okay. So, and yeah, this one is possible at the high luminosity. We can see some evidence of it. Not right now, not yet. And this one is we have seen it already. So this one is probably high luminosity. This one we have seen it already. This one we are starting to see it in the BB bar, Higgs to BB bar, and this one, yeah, maybe we are starting to see it too. So there's a if not already, we're going to see it very soon. And these two are impossible. Okay, so not only because the branching ratio is tiny, but also because if Higgs just decay to 2 jets, that is a very difficult channel for LHC to handle. Okay, so and the charm, I think, is possible later. Okay, so this is probably also a high Lumi target. Okay. What else Higgs has? So Higgs also has a coupling to gluons. Okay. So obviously you say, oh, in the standard model, this coupling is predicted from this coupling, right? But we should still try to measure this coupling. Okay. This is a way of new physics to show up. Okay. Is that this coupling, Higgs to glue coupling, is different from what's predicted from just integrating out the top quark. Okay, so that is similarly there can be gamma. Right, this is the discovery channel, and there can also be a Z gamma. Yeah.
Is the strange also too light?
Way too light, I think. Going to chaos. Yeah, good luck with that. I think. Yeah. So, okay. And this guy, we haven't seen that yet. Okay. So but we will hopefully we will at some point. Okay. So for the moment, our main target will be these fermion couplings and this coupling. Okay. So this is a very important coupling, right? This is a sort of verifying Higgs is doing what it's supposed to do. Okay. So what is Higgs supposed to do? What is it? What is the purpose of Higgs in the standard model? No. That's the job of Vev. That's not the job of the particle. What is the job of that particle? That unitarize the amplitude. That's right. Yeah. Christoph talked about it. Right. So that's the real definition of Higgs boson. It unitarizes the amplitude. Okay. Just breaking electrical symmetry and give mass, we don't need the Higgs boson. Okay. All right. So, but this is the crucial coupling that we to do it. Okay. Now let's see. Just to have some numbers. So for I think you all know the mass of the Higgs. Okay. And the largest branching ratio is to what? Which one? What is the dominant Higgs decay? Huh? To BB bar. That's 58%, roughly. Okay. So, and what's the next one? Huh? Glue is about 8%. Yeah, that's WW star. This is about 21%. Okay. And these are the biggest ones. Okay, the rest of them are so ZZ is about 2.6%. Our discovery channel gamma is 0.22%. Okay, roughly. Okay, so another important parameter is the width of the Higgs. Okay, so what is the width of the Higgs? What is? Yeah, so 4 MeV, roughly speaking. Okay, very narrow. Narrow primarily because of this coupling is very small. Okay, It's dominantly contributed from by the BB bar decay mode, and this coupling is tiny. So it's very, very narrow. So it's very different from the Z, if you want. Z is broad in this sense, okay? Because Z is just some gauge coupling, order 1 gauge coupling, but this is a very small coupling. Okay. Now we wanted to, obviously you wanted to measure these couplings by measuring the rate of a bunch of processes. Okay. So let's just go over some of the basics of how do you do it. So the rate of a process, let's call it Rj. This is in the end it goes to J. Okay. And this is sigma production. Okay, depends on what channel. You're thinking about. That there can be different production channels, times the branching ratio of the Higgs going to that J. So, but the branching ratio is this. Okay, it's the partial width divided by the total width. Okay. Now we can also, in order to measure the deviations of these couplings, it's useful to parameterize the deviation in some way. Okay. So now there are many ways. There are several popular ways of doing it. I'm just going to do the most simple-minded way. Okay. So that I'm going to say that I'm going to define kappa I as the G of some coupling, Gi measured over Gi of standard model. Okay. So this is sometimes called, so kappa equals to 1 means I agree with standard model. Okay. Not equal to 1 means that there's a deviation. Okay. And this is sometimes called the Kappa Framework. Okay. So all my serious friends, including myself, hates Kappa Framework. Okay, but you know, for the following reason, it's not very theory motivated because it breaks gauge invariance. Okay, if you think about it. Okay, but so to be really gauge invariant, one should be really thinking about I should literally add to the Lagrangian a bunch of dimension 6 operators. I'm actually constrain the coefficient of those operators. Okay, that's a much more invariant way of talking about it. But that's going to be, you know, to do that is going to be a mess. So, but let's just try to do it with this for the moment. Bear with in mind that it may not be, you know, very serious, well, theory motivated. Okay. Yeah. So typically, what are the free parameters we wanted to constrain? Let's think about it. Okay. So there is a GW, GZ. Okay. G top, G bottom, G charm. Okay. So you can keep going, and G tau, and G gluon, G gamma. Okay, you may think about this GZ gamma. Okay, so this is a and if you want, you can think about the triple Higgs coupling as well. Okay, but so I'm trying to include all the things that you can measure. Again, I'm going to treat these are independent parameters that parameterize the gamma and the photon, just in the sense that I'm allowing new physics to contribute to these vertices. Okay. And this is not enough. Yeah.
So you said kappa is not gauge invariant.
Yeah, if you deviate from the standard model just from this guy, it's not good, right? So, but you know, nevertheless, you know, you can measure it. Okay, you experimentally you can actually measure a number for kappa. All I'm saying is that if you see that kappa is not equal to 1, this does not mean this coupling literally break gauge invariance. This means that there's some dimension 6 operator that it's just a matter of interpretation. Yeah. Okay, this is not enough. Okay, you see that from this already it's obvious that in order to measure any couplings, I must know the width. Okay. I also must know the total width. Okay. Now you say, okay, why isn't total width also parameterized by this, right? I just you can giving you these couplings, you can calculate the width, right? But you should allow yourself to consider there are some exotic decays. Okay, in addition to the standard model decays. Okay, so there should be some possibility or fraction of decays is going to some exotic states. Okay, okay. Of course, we are searching for those. You should be able to look for those exotic things at RGC, but it may not always be possible. Okay, so let's say Higgs decay to 4 jets. Okay, that's totally impossible. Okay, that's just a huge QCD background, and so it's a so and also there always the possibility that there's some possible final state you haven't thought about yet. Okay, you're not looking for it. So and so the general procedure is just to include a free parameter we call exotic. Okay, and it's even more slightly more convenient is to just include a free parameter we call total width. Okay, so these two are interchangeable because once you fix these couplings and this you can calculate. Now you can really calculate this. So these two are equivalent. Is okay. So this is all right. Okay, so now let's we can think about a few processes, just to define yet another thing too. So, so the main production mode from at RGC is this. Right, the main production mode is this. So this is the final state I. Okay, so right. So let's define something. Let's define something called mu G and I. Okay, so a ratio. That this just means that this is the rate between over standard model production rate. Okay, so that's just by definition. You see that from my definition over there, and this is proportional to kappa G squared times kappa I squared. Yeah.
How can you know if it's produced by, if your final state is produced by gluon?
Huh?
How can you know that you have produced the Higgs from two gluons from gluon fusion and not from?
The quark production is this. Okay. You distinguish this by looking at this guy. There's one additional gauge boson here. Okay. Okay. Is this okay? This is because the partial width here is proportional to kappa I square. Okay. The production vertex is proportional to this square. Okay. There are some other constant. I'm not writing out everything, but.
How degenerate is this free parameter?
Hmm?
The free parameter width here?
Yeah.
How degenerate is that with the constant?
Yeah, so I'm getting there. Okay, so there is that's obviously a problem to get in the way of measuring these things. Okay. All right. So, and this what we call is a Higgs-Schlong process. So this is glue fusion. This is a Higgs-Schlong. Okay, Higgs-Schlong. You can define something similar. Okay, this is just sigma QQ bar to VH with H goes to I, right? So this is the standard model production. Yeah, this is obviously proportional to kappa V square, kappa I square. Okay, that's the. And there is a VBF process too. So these are the main mode. You can define this mu parameter for all of them. Yeah. Now, as someone already said, in order to, it's very obvious from these formula that in order to measure any coupling, I must know the width. Okay. If I don't know the width, I cannot measure any coupling. Okay. So what is the way to measure Higgs width? How do we measure Higgs width? First, okay. So first, you say that okay, the width is just the width of some Bragg-Wigner peak, right? So if I can measure this, I see the Higgs width. Okay, but it's impossible at LHC. Okay, in fact, it's impossible anywhere that I know. So this way of measuring Higgs width. Anybody knows why? Because it's too narrow, and the actual width of the peak you see are completely determined by the resolution of the particle. We cannot measure the momentum of the particle very well. Okay, so the resolution at the LHC, depends on what final object we are talking about, obviously, but it's roughly 1%. At the 1% level, okay, percent level, and the Higgs mass is 125. At the percent level, you can this peak width you see, it typically is a couple GeV. Okay, it's completely dominated by resolution. You don't see anything at that level. Okay, so that's impossible. That's not even possible at the lepton colliders. Okay, so just because you almost never get a precision that good. Resolution that good. Okay, so forget about the direct measurement. Okay, so let's think about some indirect way of trying to get a measurement of the width. Okay, let's try to do that. Okay. For that, so one way of try to do it is the following. And let's think about a cross-section of this process. Okay? And this is a very clean process. Okay, the Z can go to leptons, so you get four leptons, you can reconstruct the Higgs peak, and you can do it very well. Okay. But we can write this process, okay, as something like this. Okay. It's obviously something like this, and then okay, because it has two vertices. It has the glue to Higgs vertices, and it has a Higgs to ZZ vertices. Okay, so these are these squares. Okay, you have come in with these squares, and divided by. So again, let me draw these things. Okay, so and then there is a propagator here. Okay, propagator here. So I'll just write the propagator. Okay, that's the propagator, and times some function. Okay, and this is a known function in the standard model. I can calculate just from the rest of the S matrix. Okay, yeah, so I'm pulling out factors that's useful for us later. Okay. Okay. Now, on shell, so if I look at the Higgs production on shell, okay, so there are on shell, okay, means that S equals mh square. Okay. There, this cross-section on shell is so I'm just going to another one more thing I should say. Let me erase this. The next thing I will do is I'm going to make an approximation of this propagator. Okay. Yeah. So okay, you can show that this can be approximated by this function. When this guy is much smaller, okay? When basically, okay? So this is called a narrow width approximation. Okay, you're basically approximating a very sharp Gaussian with a delta function. Okay. And so if you can look it up, but this is actually one of the definitions of delta function. Okay, you can one way to define delta function is approaching it from a Gaussian, from something like that. So on shell is just you take that narrow width approximation, integrate over this. Okay, just delta function just picks up the so on shell this is kappa g square kappa z square mh gamma h and that function with s hat equal to mh square. Okay, so this is on shell, the rate on shell. Okay, and then the trick is to also look for this off shell. Okay, I can also look for this off shell. I can produce the Higgs off shell. The off shell means that I can ignore this. Okay, when s is not equal to that, it's very easily this factor is much bigger than that. Okay, so I can ignore the second factor. Okay, so this function right. In fact, let me look at the region where s hat is much bigger than, if I look at the region where s hat is much bigger than mh square. So I'm going to ignore this part too. Okay, so it's basically like that. Okay, if you don't, I mean, I'm not writing down the exact formulas. Okay, but this just shows you schematically how you do it. Okay, now the idea is now I'm going to take the ratio of these two guys over. Okay, the thing is, you notice that the off-shell rate does not depend on width. On-shell rate depend on width. So you take the ratio. The reason to take a ratio is you can take out this dependence. Okay, because you in principle you should also, you know, the difficulty here is if you just do it with a single one is also it depends on this rate, these modifications. But take the ratio, those things are gone. Okay, and yeah, this is gamma total. This is proportional to gamma total. So okay. So that is with known factors from the standard model. Okay. Okay, so that's, yeah.
Minor question. Why do you put hat on the sigma?
I'm integrating over possible S hat.
So it is
Yeah.
not parton level calculation.
Yeah, so remember our cross section is basically ds hat and the parton luminosity as a function of S hat times sigma hat, right? So that's something like that.
Here, sigma hat is
Yeah. Okay, I'm not responsible for the correctness of every hat, but so that interpret it whatever you want. Okay. So, anyway, so this is not exact formulas. So in the actual calculation, I think you can do a exact calculation for the. You don't have to take this limit. You do an exact calculation of the off-shell rate and the on-shell rate. The key thing is, again, this is sensitive to total width, and this is not. Okay, so
I'm skipping ahead a bit, but you said there were standard model factors in front of this R total. How well are they? Are they known?
no, these two cancel. These factors cancel.
No, you said there were
Yeah. So the standard model, you can calculate them. So it's these functions,
how precisely?
as precise as you want.
Okay.
Okay. It's a perturbative calculation. Okay. So right now, as we will see, we're not even close to use this to actually measure it yet. Okay. So let me just say a few things about this. This looks great. Okay. Except this is very difficult. To measure this is extremely difficult. Okay. This means that you are going to look at the ZZ. So this means that you are going to look at the ZZ invariant mass, for example. Okay, it's something like this. Okay, and you are going to see that there's a little bit like this. You see, this is coming from the Higgs. Okay, so the Higgs rate is a completely subdominant part of the standard model ZZ in the continuum. Okay, so that's very difficult. Okay, that is number one. Number two, going back to your question, is that it's not really assumption free. Okay, it's assuming that these factors are known. It means that assuming that these factors are standard model. Okay, but in fact, if you think there are something new physics actually mess up with the total width and so on, these factors will actually sometimes, at least many times, these factors are actually going to be changed too. It's not completely standard model. There are other light degree of freedom around. So you actually don't really know that well. To make this to make this measurement, actually make additional assumptions. It's not a totally model independent determination of Higgs width. Okay, it's a way to try to get a measurement. Okay, you if you agree with standard model, you're happy. So okay, so it's consistent with your assumptions. But if it disagrees, then it's unclear it's unclear whether you're actually measuring a width or you're seeing a deviation from these functions. Okay, but if you disagree, then anyway, where are we? So the current status. Okay, current status from this measurement, the claim. So they haven't seen anything yet. Okay, they haven't seen anything yet. The claim is that the gamma total is less than about 5 times gamma standard model, gamma H standard model. So that's the claim. Okay, so there's already a bit sensitivity. Maybe with more statistics, we can hope to actually get to somewhere around the standard model. Okay, that's right now the claim. Okay, I think we have to all decide for ourselves whether you believe that claim or not. Okay, because until you make an observation, I'm not sure. So because again, it's a very difficult measurement. Okay, and you can always set a limit. It's pretty safe to set this kind of limit. Okay, so but anyway, at least in the foreseeable future, I don't expect we actually get a Higgs width measurement from the LHC. That's the bottom line. Okay. Now, coming back to my earlier comment that now you're in somewhat kind of a trouble, right? You cannot really measure Higgs couplings unless you know the width. Okay. So therefore, we come to this very important conclusions that almost all the Higgs coupling measurement at the LHC, you need to make assumptions. There's no way to not make assumptions and measure Higgs couplings at the LHC. Okay. Okay. So now let's make assumptions. Okay. Let me just make the simplest assumption. Let me just demonstrate to you for example, with these assumptions, how you do the measurement. Okay. Let me make the assumption that. Let me make the assumption. Oh. Let me make the assumption that there is no exotic decay. Okay, let me just quickly make the simplest assumption. Okay, so that's one assumption you can make, okay, at least. Right. And that's the assumption that typically makes when you see figures that people in the collaborations that actually produce measurements of Higgs couplings. That is the assumption they make. Okay, so it's okay. Now, then after that, then you can see that in principle, I can do a fit with the parameters I did and with the decay mode. Okay, I can do a fit. And the fit will spit out a precision about what kind of deviation of kappa. So that's what actually you do. Okay, that is exactly what you do. But in order to understand some of the numbers, let me just briefly show you that a simple-minded way of trying to estimate one of the precisions. Okay. Now, suppose for that, let me make a further assumption. Okay, let me make a further assumption just for the convenience. Okay, let me say gamma total is just gamma v plus gamma b. Okay, these two are the dominant part, anyways. Okay, so let me just say that. Okay, otherwise my algebra becomes longer, so the principle is the same. Okay, so okay, let me try to measure kappa g. Let me try to measure this. Okay, let's understand what is the precision of how well you can do this. Okay. Now with this, with these, okay, with these formulas, you see that the kappa g. Well, let me write this slowly. Okay, let me mu g v plus mu g and b. Okay, let me calculate this quantity. Okay. So this is 1 over sigma standard model sigma glue to h, right? That is the mu times gamma v over gamma total. Okay, so this is and plus plus the same thing basically. Gamma b plus gamma total. Okay, so measure these two rates. They depend on my parameters in the following way. Okay, and these two add up to 1 because of my assumptions. Okay, because my assumption here. And but this guy, so this guy over this guy is just kappa g square. Okay, this is kappa g square. Okay, so the idea is that now I can measure the cross section of these two guys. Okay, I've conformed this thing and add them together. I get a measurement of kappa g square. Okay. but it's not very okay. Okay. Mostly because this guy is terrible. Okay, this guy is glue to H to BB bar. Okay, that's impossible. Okay, that you basically your final state is 2B jet with invariant mass of 125. Okay, that's overwhelmed by many order magnitude by the standard model QCD background. Okay, that's soft jets. This. Okay, so this is not possible. So we cannot use this. Okay, but we can try to do something else. We can still try to do something. Okay, so we wanted to actually, what is this? We wanted to get to this guy. Okay. But we can take into account a few things that I could actually measure. Okay, what are the things I can measure? What are the things I think I can have a hope to measure? Okay, I can measure this. This one I can do it. Okay, after all that's my discovery channel. Okay, we can measure it pretty well. And I have a hope. Well, I can. So this one we have already start to see it now. So with more data, I have hope to measure this one to some reasonable degree. Okay. So this can be W or Z. Okay, this one I can do it. Okay, so if you want, in my notation, this is the mu G gamma. This is mu V gamma. Sorry, mu V B. Sorry. Okay. And we actually also be able to measure this one as well. This one is possible as well. Okay, it's a smaller rate, but it's very clean channel. Okay, so this is mu V gamma. Okay, so I can measure these three. Okay, now using my definition, you should be able to show okay, there's something I cannot measure, but it can be treated as three things that I can actually measure. Okay, so well, it's pretty easy to show. This is there's a kappa b here. There's a kappa gamma here, right? So and the kappa gamma cancels the kappa gamma here, and the kappa v cancels kappa v, and then there's a kappa g here. So this is essentially kappa g b, kappa b. Okay, so that is pretty easy to see. Okay, that's the case. So okay, now the idea is that I'm going to replace this with that. Okay, so the mu gv plus mu vb mu v gamma mu g. Okay, and yeah, now we cast everything into the something that I can measure. Okay, so also you notice that there's a ratio here. The ratio here is very good. It means a lot of systematics cancel in measuring this ratio. Okay, so this is actually fairly good measurement. And so let me just maybe I'll write it here. So at a 3 inverse Edelbaum, the projected and this guy is about 7%. Okay, the accuracy on this, and the projected of this is about 5%. Okay, so you see that if you add these two, if you just add these two in quadrature, okay, assuming this error is very small, it's pretty small. Okay, but maybe add on top a little bit, you should get a kappa g accuracy to be about 8%. Okay, 8 to 9%. Okay, so, and of course, you know, you wonder whether this is the unique way of getting to this. It's not. Okay, there are other ways to get this. Okay, this is one of those chains you can get to this. There's other combinations you can form that it's also a kappa G. So you have multiple channels, and the actual the final result obviously is coming from a global fit to all of these. So if you add all channels, it turns out high Lumia RHC can measure this down to about 5%. Okay, so this is about you know, I show you this is probably one of the best ones to constrain this. So this is a okay. So you see that it's 5%. Okay, so it's more or less getting to the level that our target is. Okay, our level target is 5%, and it turns out many things can be measured down to about 5%, but not much better. Okay, so there's some limiting factor here. So there are certain channels you cannot really measure very well, and that actually affect accuracy of a lot of the other things. You see that in order to the accuracy of measurement of this guy depends on a bunch of channels. So all there needs to be is one bottleneck with some larger error bar. Then you just you know, your error is eventually determined by that bad channel. But yeah, it turns out a lot of the couplings can be measured down to the 5% level at the RHC. Okay. Okay. Now I'm going to switch gear to talk about Hicks factories. Okay. So let's see why Hicks factories does better than this. Okay. So. Okay. So Higgs factories. Higgs factories are E plus E minus colliders. Okay, there are many options being proposed. There is something called the International Linear Collider. That's you know, we'll see whether they are going to do it in Japan or not next year, I think. And then there are circular colliders. Okay, it's FCC EE, which is the project being proposed in Europe. Okay, it's called the Future Circular Collider EE. Okay. I think one thing certain about this project is that this is not going to be the name of the collider. Okay, it shouldn't be called a future collider. Okay, anyway, so it's and there is also a CEPC, which is a circular electron-positron collider. Okay, it's being proposed in China. But these are the things, and I think to some extent, click as well. Okay. But the click runs at a somewhat higher energy. Okay. Now the workhorse process at the Higgs factory is this one. Okay, it's the Higgs-Strong process. Okay. So what's the center of mass energy that we need for a circular collider that can do this? Okay, so this is 90, and this is 125. So you would think it's 215, but it turns out 215 is not good enough. Okay, so 215 is right on the threshold. Right on the threshold, the rate is 0, as we reviewed yesterday. Okay, there's always an opening up of the threshold. Two-body phase space, it opens up quickly, but still not literally on the threshold. Okay, so the rate goes like this. Okay, at a very large energy, the cross section just goes like this. So this is like a 1 over at a very large energy. Okay, you can ignore the Higgs mass, basically. You can ignore the mass. So the rate is just, and this is the only dimension for number, so that the rate goes like this. Okay, So there is a peak of rate, and that's 240 GeV. Okay, so this is basically where the circular collider and the ILC plan to run their Higgs mode. Okay, in detail, I think this is 250 they propose, and this guy is probably 240, and this is probably 250 too. Sorry, this is 240, this is 250, these are 250. Okay, so there's subtle reasons that but the difference is not big. Okay, so it's a tiny difference. We're going to just ignore that. Okay. Sorry, the peak, I should say, peak is actually at the 250. It's more like 250. Okay. Now, well, there's also other channels. Okay, like this. Okay, you can have E plus E minus, and W go to a Higgs. Okay, you can have this channel too. Okay, in principle. Okay. And this is very small at this level. Okay, so the rate for this, so this is called the VBF. Okay, again VBF. The rate for VBF, it's a three body phase space. Okay, so it opens up very slowly. Okay, as we reviewed yesterday. So it's something like this. Okay, it's very small. For these Higgs factories, then of course their run plan is always slightly different. No, it's not. It's slightly different, but it's always on the order of million Higgses. Okay, so it's much less than the number of Higgs produced at the LHC. Okay, LHC we're talking about billion Higgs in the end. This already produces tens of millions Higgs already. Okay, LHC is already more than this. Okay, so LHC is the real Higgs factory. This is not actually the Higgs factory. But the benefits is this is very clean. It's not that they produce more Higgs. Okay, the LHC is dirty. Okay. Now let's see, how do I see this Higgs? Okay, in this mode, how do I see this Higgs? Okay, let me just draw this diagram here again. Okay. The idea is to do the following. Okay, so, and this guy goes to L plus L minus, for example. Okay, so I'm going to use this. I can solve for the full momentum of Z. Full momentum of Z. Okay, I experimentally, I know the full momentum of Z. Okay, and the E plus E minus, I also know the momentum of these guys. Is that okay? I know the momentum of this guy, I know the momentum of this guy. Okay? So I know PE minus plus PE plus. I know these two for moment. Okay? Now I'm going to make this minus that. Okay? And that is just the momentum of the Higgs. That is the full momentum of Higgs. Okay? I'm going to make this square. This is just the full momentum of Higgs square. Okay? And this guy, this is the so-called recoil mass square. Okay? And obviously, if you make the recoil mass distribution, because it's just a Higgs momentum, you will have a peak around the Higgs mass. Okay, so you will have this, or this is M Higgs. Okay, so that's the idea. So I'm going to take this event. I'm going to look for a z. Once I see a z, I'm going to make this recoil mass distribution. I'm going to calculate that recoil mass for that event. If it falls in the Higgs window, I'm going to call this a Higgs event. Okay. Okay. So you see the benefits of this. Okay. This is a way of tagging this Higgs event without looking for Higgs decays. This is independent of however Higgs is decayed. It can decay to anything. It can decay to 20 black holes. It doesn't matter. Okay, you can just you just do this. Okay, and compare with the LHC, obviously you see that's much more simpler, right? So there's not that all these fancy things I need to do with branching ratios and so on. I don't need to do anything here. Okay. And so this gives you a model independent determination of kappa z. Okay, immediately. Okay, model independent of the width. Yeah.
But in the same way, if you measure Higgs production not by branching ratios or whatever, doesn't it also make it harder to measure the properties of the Higgs?
No, this will be the one that this is the. So all I need is one model independent number usually. Okay. And with that, I can anchor all the other things. That's the idea. Okay. So I haven't talked about all the things yet. Okay. So that's one model independent number. So if I have a couple of model independent numbers, then maybe I would be able to anchor the whole measurement. That is yeah. So and lepton colliders also don't have error bars. Okay, but that's not true. But they more or less don't have error bars. Okay, so they are statistical dominated. Okay, they are statistics dominated. Instead of LHC is always systematic dominated. Okay, not always, but eventually they will always be systematic dominated. So statistically, you can already see that this can be measured this down to about 0.2%. The kappa z measurement. It's also much better than what LHC can do, which is 5%. Okay, sorry, yeah.
Maybe directly onto this accuracy. And how does new physics come into play?
Well, new physics can modify Higgs z couplings, right? So all those dimension 6 operators you write down, they can always a lot of them can modify Higgs z couplings. Okay, 3-4 of them can measure. Yeah. Yeah, you will be sensitive to those, but again, a better way, at least to our theorists, is to actually do a global fit with those operators. Okay, but this is just but still, even that this process will give you a very nice constraint. You already see that. Yeah. Okay. All right. Now again, let's think about measuring width. Okay, measuring. Remember, I still have in order to go from this to others, I still have to know the width. Okay, don't forget about the width. Okay, so let's think about the width measurement. Okay, so there are a few ways you can do the width measurement. So the first way is to do this. You certainly have this process. Okay, it's a small statistics. Okay, because this branching ratio is just about 2%. Okay, it's a small. Okay, and then if especially if you all still wanted to look for leptons, that's even smaller. Okay, but maybe you can live with some jets too. Okay, so because lepton colliders, again, you see everything you can produce, you see it. Okay, well maybe not. Even dark matter pair production, you can probably see it. Okay, but as long as you have something else, but everything you can see. Okay, so in principle you can use the full statistics of any z decays you want. Okay, so the concept of doing lepton colliders is very different from hadron colliders. Okay. But if you let's write this in terms of widths and the couplings. Okay, let's write this as widths and couplings. So first of all, you can write the total Higgs width as partial width of this divided by branching ratio of Higgs to ZZ star. Okay, so that's just definition. By definition, there's a definition of that branching ratio. Okay, and this is just the Higgs ZZ coupling. Okay, this is determined by the Higgs ZZ coupling. Okay, the upstairs, but Higgs ZZ coupling is the one that I measured very well, independent of width. Okay, I measured it very well. Okay, so let's see. This is my really just proportional to this cross section, not square. It's just the cross section. Okay, so divided by branching ratio. Okay, but this I measure. Okay, by just measuring the rate of this. Is that okay? So this is just I know the rate of this. Then I measure the rate of this. I know that branching ratio. Is that okay? Yeah. So that's one way to model independently and measure Higgs width at the lepton colliders. Okay. It's one way, but sometimes it's not too good because of the small statistics. Okay, but nevertheless, it's a model independent measurement. Okay? You can do it actually pretty well, down to a few percent. Okay, it's not bad. Sorry. Where did that go? Oh, okay. And this can help too. This guy can help too, actually. So what you wanted to do is not this. What you wanted to do is just to do this. Okay. So this way you write gamma h as gamma h to BB bar divided by branching ratio h to BB bar. Okay. Again, this is just definition. And you recognize that this is just a sigma VBF to h to BB bar over okay. So again, you form this combination. You can measure these things very well. Again, from the Z process. Okay, you can measure these branching ratios very well. Okay, just by looking for these things. Okay, with this process, you can measure these branching ratios very well, and this is the rate of this VBF process. Okay, so this accuracy is pretty much depending on the accuracy you can measure about this process. Okay, and that is the point. And so this gives you another way of determining the Higgs width, and this is the process actually. You benefit from actually going for higher energy lepton colliders rather than 250, because the VBF process really picks up, if I have a 500 GeV ILC, it will actually measure the width even better. Okay. Okay. So now I have a really model independent measurement of this coupling, and I can. Also have a model independent measurement of width. I can model independent measure everything, okay, at the lepton colliders. So that's the idea, and at least for this coupling, to a much better accuracy than what the LHC can do. Okay. So let me again make a comment. So LHC is very useful in terms of Higgs measurement. By looking for the Higgs, very rare Higgs decay mode and a very clean mode. If it's a very clean mode, LHC has a clear advantage because it just produces more Higgs. And if you can see them, then it's very good. For example, Higgs to mu mu. Okay, LHC can actually do very well. But lepton collider, clearly you can do this standard measurement very, very well. Okay, for the so if you want this, if use our formula earlier, this is translated into 5 to 6 TeV new physics scale. Okay, this is translated into the, and this is entirely out of the reach of the LHC, I think. Okay. Yeah, what else? So yeah, so in the lecture notes, I actually have more figures, but this is the basic idea about yeah. Right. Yeah. Go ahead. The WW is canceling the WW factor here. Okay, so there's a factor here depends on WW. WW coupling.
Yeah, because we have WW going to Higgs.
Yeah. Yeah. So you wanted to cancel that in order to this to be independent of the WW coupling. Yeah. Again, you can try this with kappas, and you see the kappa W cancels, right? Kappa W on this side cancels, and then this guy. But this guy is just a total waste. Okay. The key thing is still I can measure these numbers very well, model independently. So I can from just from this process. Okay, from the Z Higgs process. Okay, I measure those things very well. And then this accuracy on this is just determined by this cross section, basically. Okay. Of course, I mean, in the end, this is not what you really do. What you really do is to do a global fit. Okay, but this is a way to convince yourself you can actually make a very good measurement. And your global fit will be mainly constrained by this constraint, anyways. So. Okay. So maybe I will just say a few words about the triple Higgs coupling. Okay. Triple Higgs coupling is very interesting, very important. Okay. It's important in the following sense. Okay. So in the standard model, the Higgs potential is very simple. Okay, I think Christoph must have already talked about it. Okay, you have this, right? So you do it here, and the second derivative determines the mass of the Higgs, right? And this is the VAV, and the second derivative determines the mass, and the third derivative determines the third derivative around here determines the triple Higgs coupling. Okay. But it's probably useful to remind ourselves. Okay, this is not what we know. Okay, this is just a simple model of what we it can fit data, but this is just simple model. So this is what we know at this moment. Okay, we know there's a VAV. We know this mass. Okay, we don't know what the rest of it look like. Okay, just to, and yeah. And one way to distinguish this, there could be other pictures of what the rest of it look like. Okay, they can be you can have a, you can. Well, I won't be able to draw this very well. It can look like this, for example. Okay. In terms of Lagrangians, this is the Mexican hat, right? So this is the other one. Okay, I just have to flip the sign of lambda, and this is this one. So for this one, the mu square is less than 0. Lambda square is bigger. Lambda is bigger than 0, and this one I just have to this other one I just have to make this greater than 0, this less than 0, and then the lambda 6 will pick it up. H to the 6 will pick it up. So at this moment we have no information that we can distinguish these two. Okay, at this for the moment. And so a way to distinguish these two is to measure triple Higgs coupling. And the physical consequence of difference between these two is that in the yellow one you tend to have first order electric weak phase transition, and in the white one you don't. Okay. So if you're a big fan of electric weak barogenesis, you better hope that. Anyway, that's not the only ingredient you need for barogenesis, but it's actually one ingredient. Okay. So at LHC, what you do is you hope that this process can give you some hint on the triple Higgs coupling. Okay, that is your hope. Okay, and unfortunately, at LHC there's another process. Okay. And these two interfere, okay, and destructively. Okay, so, I mean, it doesn't even matter whether destruct or construct. The first point is just, first of all, these final states are very difficult. The rate is small. Rate is very small, and these final states are difficult to tag onto. Okay, so perhaps the best channel people thought about is BB gamma gamma. One of them goes to 2B, the other one goes to gamma gamma. Okay? So you say, why is that? Okay, why can't I use the channel with the most statistics, which BB, 4 Bs? But that's impossible. Okay, 4 Bs, 4 not very energetic Bs. That's also known as QCD, right? So QCD, you just have a B factories there. Okay, so there's lots of Bs. Okay, so you it turns out it's better do you actually pay the branching ratio to go to a cleaner channel. Try to get some handle on it, and but even if you do, you see double Higgs production. Okay, right now the challenge is to whether we are going to ever see it or not. Okay, but even if you see it, you still have to disentangle these two. Okay, so right now the projection for high luminosity LHC is not very clear. Okay, there depends on who's doing the study and so on. So, okay. But the accuracy is about order 1 at high luminosity LHC. Okay, certainly not right now. Now at 100 TeV PP collider. Okay, if we have a 100 TeV PP collider, and we suddenly have many more rates on this. The projection is that you can probably measure this down to 5 to 10%. Okay, so that's sort of reasonable. Okay, also at the lepton colliders. What you can do is you can do this, for example. Okay. And that's not the only diagram, but lepton collider is very clean. Hopefully, but the only thing is that the 250 is not enough. Okay, it turns out the 500 is not even quite enough. Okay, but you probably a 1 TeV ILC, okay, can make this down to about 10% as well. Okay, so okay. All right. So let's see. Let me make one more comment. Okay. So but one thing you see that you see that if I do have a potential look like this, okay, I wanted to really change the picture of phase transition. Okay, I wanted to go from the Mexican hat to this different kind of hat. This term must be at least as important as this term. Okay, this means lambda needs to be small. Okay, this guy needs to be small. This means whatever new physics you integrate out, and then its effect is actually pretty big. Okay, and by writing this, I'm making the assumption that this new physics only show up here. That's the only way this new physics show up, which is very unlikely. Okay. So Let me just make so for example, suppose I have a very simple model. Okay, let me just write a very simple-minded model. Okay. Okay, let me just add a singlet. Okay, I'll just add a singlet. Okay, in fact, let me just add that. Okay, no, maybe I will add a cubic coupling and so on. Okay, let me just do that. Okay, so for that model, you see that once I integrate out the singlet, I do generate this. I generate this guy. Okay, this cubic coupling is generating this guy. So there I have a cubic coupling of singlet. So let me do this. Use solid lines for singlet, and then Higgs. So this gives you a h to the 6 coupling. Okay, that does give you this. Okay, but for the same model, you also have the following singlet, right? So just again, I'm using this vertex, and this guy. After you integrate out the singlet, well, I give you the h to the 4th, but that's the first order. The second order, the second order in derivative, you generate a dimension 6 operator, which is this. Okay, and this, of course, once this Higgs gets a VAV, it's just a wave function renormalization of the Higgs kinetic term. So you have to canonical normalize the Higgs again. Okay, when you canonical normalize Higgs again, you generate a coupling between the Z and H. Okay, at least. Okay, and on the order of V square over lambda square. Okay, very similar. Okay, so, but this, remember, at Hicks factor we can measure them down to 0.2%. Okay, so in fact, any this kind of model, typically you will see it from the first indication of it at the Hicks factory as well, just from the deviation of C. Okay. So, in fact, the most naive model you write down to generate this, and actually give you the deviation both on the triple Higgs coupling and the Z Higgs coupling at the same order. Okay, at the same order, and that is already constrained. Okay. And the high luminosity LHC can also constrain quite a bit of it already, just from the 5% measurement on the Z Higgs coupling. And for 0.2% measurement of Z Higgs coupling, you can probably cover most of the models. Okay. So, okay, I guess I will stop now, and we'll talk about dark matter tomorrow. Okay, dark matter LHC tomorrow. Okay.